This is Isaac Physics question I3.1. It's the question that is the first one about discharging capacitors. So in the question, we are given the capacitance and we're given the resistance, and we've got to work out the time constant. Well, the equation for the time constant is CR. So I'm just going to simply stick in the C value being 100 microfarads, so times 10 to the minus 6, times resistance, which is 200 kiloohms. And that gives me a value of 20 seconds. So it takes 20 seconds to get to 37% of its initial value for the voltage or the current or the charge. That's part A. Part B is to work out the halving time, and the halving time is the halving time, you call it the half-life, is equal to the time constant times ln2. So I'm just going to stick in my values. I get 20 seconds times ln2, and I'll show you what that looks like on a calculator. So we've got 20 times ln2. We get 14 seconds. This is the work solution to Isaac Physics question I3.6. It's a very difficult question. So part A, we are asked to find the initial discharge current when a capacitor of 2,200 microfarads is charged with a 12-volt battery, and then it's discharged through a 10 kilo ohm resistor. So first part, all we have to do is V equals IR. We've got to work out the initial current. So the initial current is going to be V over R. And the voltage will be 12. The resistance will be 10 kilo ohms. So 10 times 10 to the power of 3. And that equals 0.0012 amps. Part B, the question says, calculate how long the capacitor would take to discharge if the initial rate of discharge were maintained. Now, this wouldn't actually happen because in real life, a capacitor would discharge very quickly at the beginning, but then it would decrease, so we get this exponential decay. What this is saying is, imagine it's a sort of constant current, so a constant rate of discharge. So here, what we're going to do is we're going to use I equals Q over T. So what I want to do is I want to work out the time it takes. So I'm going to do Q over I. And I know I from before, but I don't know Q. So what I'm going to do is I'm going to use the capacitance equation, which is C equals Q over V. And I'm going to rearrange that to get it as Q equals CV. And then I'm going to plug in the values from the question for capacitance and voltage. So I do 2200 times 10 to the minus 6 times the voltage, which was 12, and I get a charge on the capacitor, an initial charge of 0.0264 coulombs. So, working out the time, I'm going to plug that in for the charge, the amount of charge that has to leave the capacitor. So we've got 0.0264 divided by the current on the initial current, which we're assuming is constant for this part of the question. And that gives us a time of 22 seconds. So it's saying if it didn't decrease in current as it discharged, it would take 22 seconds to complete discharge. Part C. Here we're asked to calculate what the voltage would be across the capacitor after 22 seconds. So this time now is where we are going to start using this equation with our exponential. Because here we're not making any of those nice easy assumptions. So we're asked, what will the voltage be when the time is 22 seconds and V0 is the initial voltage of 12 volts. So what I'm going to do, I'm going to plug in my values and I'm going to plug in V0 is 12. I'm going to make this nice and big so you can see what I'm doing in the exponential. Times e to the power of minus t, so t is 22 seconds, over R, which was 10 kilo ohms, times C, which was 2,200 microfarads, so times 10 to the minus 6. And I plug that all into my calculator. So that in my calculator would look something like that. You can see there I've got all of the terms nice and laid out. And that gives me 4.4 volts. So after 22 seconds, the voltage would be 4.4 volts. Part D now. I have to work out what the currents will be when the voltage across the capacitor is halved. So the initial voltage was 12 volts. So the voltage when it halves will be 6 volts. And I have to work out the current at that time. So I'm just going to use V equals IR again here. I'm going to rearrange for I, and I get V over R. V is the voltage, so it's 6. R is the resistance, which was 10 kilo ohms, so 10 times 10 to the power of 3. And that gives me 6 times 10 to the power of minus 4, or on Isaac Physics, 6e to the minus 4 amps. Now finally, this is the hardest part of the question, part E. In part E, we now have to calculate how long it will be, how much time will it take before the capacitor has a voltage of 3 volts across it. So I'm going to use this equation again. Minus T over RC. And here I know what the voltage is, so I'm looking for a current voltage of 3 volts. The initial voltage is 12 volts, and I want to work out T, how much time has passed. And I know R and C, they're still the same as before. So what I'm going to do, I now need to get this equation as T equals. For those of you that do maths, you might be a little bit more comfortable with this, but for those of you that don't, I'm going to have to be using some logs. So I'm going to rearrange this now to get V over V naught equals e to the minus T over RC. And then I'm going to take the natural logarithm of both sides. So that will give me ln V over V naught equals ln E minus T over RC. Now, when I take the natural logarithm of e to the power of something, the ln and the e sort of cancel each other out. So what I'm left with is I will get ln V over V naught equals minus T over RC. I then want to rearrange for T, so I'm going to bring the RC and the minus sign to the other side, and I'll end up having T equals minus RC times ln V over V naught. I'm going to plug those things into my calculator, where R was my resistance, 10 kilo ohms, C was the capacitance, which was 2,200 microfarads. The current voltage is V, 3 volts, and the initial voltage V naught was 12. So I'm going to plug all those things into my calculator, and the answer I get is 30 seconds.